for IJGIS authors. And again, the monthly webinar, our intent is to offer the opportunities for IJGIS authors and readers to have a conversation on the topic that we see have attract a lot of attention based on the publications. And you can see that on the screen. Our topic today is about how to establish the integrated science or movement. And before the seminar, we were checking that movement is such a popular topic right now as a logical transitions from location, time to trajectories. And in fact, these screenshots that maybe a little bit outdated, it only showed 2,962 views. And I just checked today, it's already over 3,000 views on this particular paper. As you can see that it actually just published online in February this year. So it is quite delightful that this paper have attract pretty good attention and also already have 4 citations. And I hope that throughout this webinar, we will be able to have a more in-depth discussion with the author on the essence and directions of such a integrated science or movement. Our speaker today are Dr. Uzka Dexard, and she is an associate professor at University of St. Andrews. I think she is also a director of a research center on data science. And Professor Jack Long, and he is, I think you are up to renew this year, so you probably already associate professor now at the Western University in Ontario. We know that Western University is one of the landmark universities in the overall history of GIS development, with Goodchild and David Mark started at that university. So a lot of traditions. And then I'm very glad to have Dr. Long here that represent that tradition, and then will make a big jump from the historical recognition to even future development of GIS at Western University. Then we have a early career scholar, Professor, I have trouble to pronounce her name, but she said that I can just call her Shiwa. And she is at New Zealand. I'm sorry, she's at University of Auckland, New Zealand. And recently I have seen that a lot of good submissions and outstanding researchers from New Zealand. So we are really happy to have the connection to Siwa, and hope we can see she is a pretty good writing star there. And then we hope that throughout the connection, we will really build the international collaborations among GI scientists on this topic. So without further ado, then I will have Uzka to get started of the presentation. And I have mentioned that in the chat, the speakers have prepared some questions that they would like to discuss with the audience and after the presentation. So please take a look at those questions in the chat, and then think about what you will contribute in the thoughts and ideas. So Uzka, please take over.
Yeah, thank you, May. So yeah, what we are going to do here was that the 3 of us, so me, Jed, and Shiva, are going to each present certain parts of this paper, and then we thought we would have a broader discussion with the audience. So as May said, please have a look at those questions. But before I start talking about the actual integrating science of movement, I would like to acknowledge all the people who actually contributed to this, because it wasn't just me and Jed and Shiva, it was also our research team members and colleagues. So these are all the people that you can see on screen now. So I would just like to acknowledge their contributions as co-authors of this paper. So you might wonder what is actually integrated science of movement, and what do I mean when I say that? And I'll get to that. But before I do that, May already mentioned that movement data are basically everywhere these days, right? So you have your mobile phone gets tracked, you can generate flows of mobile phone connections from this. You can have apps that track your car and tell you how much fuel you spent and how far you're driving and so on. You can put your fitness watch on and you go and bike around London, and you can create a nice trajectory that resembles an animal that you then put on Strava, and you can see this on the map. You can also track real animals, so ecologists put trackers on all sorts of animals. I'm just showing here some examples with birds, where you can track the migration, let's say, from Germany down to Spain. You can also track, or people also track any kind of transportation, so anything from airplanes to trucks to ships to anything. So basically everything and anything is being tracked these days, which generates movement data. So you have a lot of different kinds of groups or different kinds of people who are interested in movement. That you can probably see just from these few examples I put here. And so in this paper, we looked across all the disciplines that we could think of or we could find that were interested in movement. And for this presentation, what I thought would be really interesting is to just sort of put a timeline on this, to try to see when these kind of analysis and when this kind of interest actually started. And this is the chart that I came up with. So I have how many? 7 different disciplines there, or 6, 7. Ecology, and then geography and geoscience. I put those together, transportation science, public health research, and then I have methodological disciplines such as computer science, location-based services, and physics. And if you look at the timeline of this, you will notice that even though, like May said, analyzing movement is kind of a new thing, it actually isn't. Because in some disciplines, in those where movement is the focus of study, so like say movement ecology, which focuses on movement of animals, these things can go way further back. So even 200 years back, if you want. So the first in ecology, you can start with bird ringing. So putting rings on the legs of the birds, and then you note where this same bird was observed and what time and the location. And this started in 1803, right? And then if you look at geography and cartography, right, there are maps of flows of transport between or different countries and export and import between different countries in the second half of 19th century. So again, this goes way back, and it's not a new thing. So on the other hand, the methodological disciplines, so computer science, LBS, physics, only come in at about year 2000 or so. And looking at this, I think, and we think, because I discussed this with Jed and Shiva, that the main reason for this is that the GPS, as we know it today, so as an accurate tracking tool, became available in May 2000. It was available before, it was available since 1983, but at that point, because GPS was a military constellation from the beginning, well, still is a military constellation of satellites. So in 1983, the signal was open to civilians for the first time, but it was actually intentionally degraded so that the accuracy was worse for civilian applications. And that only stopped in 2000. So this thing, this action, along with the development of new tracking technologies, is what then caused this giant explosion of GPS data and led to the interest of movement analysis in these methodological sciences. So the question then is, if you look at all these different disciplines and if you look at different studies, and what they look at is how you start thinking about, oh, I've seen that before, but it wasn't in this discipline, it was in another discipline. And then you start looking at all this in more detail. And it turns out that there's actually a lot of things that are very similar. Maybe they're called something else, but conceptually and mathematically, they are just basically the same thing. And so a few years ago, this kind of interdisciplinary discussions started in Europe. This was spurred by the cost action move, which was run by Rob Weibel, who brought together all these different disciplines, people together into a network that ran for 4 years. And in the US, it was Harvey Miller and Jennifer Miller and Somaya Dodge and various other people who also sort of had their network, and they had, I think, several workshops and so on. And people started looking at what is actually, how it would be possible to actually bridge this gap, to bring these disciplines together. And specifically, the focus here was on bridging the gap between analysis of animal movement and analysis of human mobility. And a couple of years, so this is 2 years ago, right? 2 years before our paper, this paper came out by Harvey, Somi, Jennifer, and Gil Borer, who is an ecologist. And they tried to answer this question. So is a transdisciplinary science of movement that is useful for both animals and humans possible? And how can we achieve that? And so their approach was to get together groups of experts and discuss this and sort of have a top-down approach. But it still led to this question. So how can we really do it? I mean, you can have the opinion on how people's opinions and how this can be done, but the question is, how can we do it practically? So what we then wanted to do in our paper, or what we saw that there was a gap or a need for, was how can we do this not by talking to experts, but actually looking at the literature and first studying what is and isn't similar, and then try to build a unifying theory from everything that we found. And so this was what led to our paper. And this paper basically structured around three main topics. One is a general paradigm, which I will describe in the next few slides. The second part, which is possibly the most interesting if you are new to movement analysis, because it sort of reviews everything that there is in both animal and human movement. So we looked at similarities and differences, and Jet is going to talk about this. And this is in supplementary info 1 if you want to read it, or if you want to give it to your PhD students. And then finally, we were also looking at what are the challenges that are coming and what are the emerging trends, and Shiva is going to talk about that. And after we're finished, so as we proceed through this, you will see that there are several questions interspersed on the slides. And at the end, what we would like to do is to have a wider discussion with the audience based on these questions. And these are also the questions that are in the chat, like May said. So I start first with this general paradigm, but before I do that, I also want to describe this basic conceptualization, which may not be familiar to you if you are either an animal ecologist or a human mobility expert, which is how do we actually represent movement? And there are two ways to do that. One way is to look at movement as a property on an individual. So you have an individual who is moving from one location to another, and you then record these locations, and that results in trajectories. I have some examples here. So here on the left, I don't know, can you see my mouse? No, probably not, right? I think I need to change it to, maybe if I change it to a laser pointer, can you see this now? Yes or no? I cannot, somebody's typing, but you have to tell me because I cannot see the chat.
We can see your laser.
Okay.
Yes, we can see it.
So you get trajectories, you have sequences of locations with a timestamp where an object or an individual was. So here there are some gulls flying in the Netherlands. You can have these in 3 dimensions. So here we have some Antarctic petrels nesting on the mountains. And people, and the common way for analysis of trajectories of people is then to add various properties to that. And this kind of analysis that's based on an individual, of a movement of an individual, is called Lagrangian analysis. On the other hand, we can also look at movement as a property of space or population, and this means that we don't actually know how each individual is moving, but what we know is how many things or how many individuals move from one location to another. And a typical example is something like this, which is a typical like geography example. This is a commuting network, and what this basically shows is that you have all the data zones shown as points on the map of Scotland, and then each connection between 2 points tells you how many people commute from one location to another location. So This is a so-called origin-destination flow. So you have an origin and you have a destination and you have a flow in between, how many people are basically flowing from the origin to destination. And this is all over human mobility. Mobile phone data are come in this type. You can also look at things like bike share data. So here I have an example where I have stations of bicycles in London, and then here the flows are then from one station to another are shown in a space-time cube over a week. So you can see 7 days of patterns. And similarly in movement ecology, this kind of data are created in marine environments, where ecologists set an array of microphones under the water and then tag sharks. In this case, I have shark data here, and you have then flows, again, in space-time cube. So this is time showing how sharks move from one microphone to another. So, and here you don't have individuals, you just know that like a group of, or a number of individuals went from A to B, from origin to destination. And this kind of analysis using this kind of data is called Eulerian analysis. So with this distinction in mind, we looked at what kind of existing theories already there are in both animal movement and human mobility. And animal movement was actually easy because there is just one general paradigm, which is very famous. It was introduced by Ran Nathan in 2008. He's a famous ecologist. And if you go to movement ecology conferences, at every slide you see the screenshot of this picture here, which is the description linked for or suitable for Lagrangian analysis, so for individual movement. So what he did in this is that he conceptualized this framework based on 3 questions, right? The first question was, why move? And in terms of animals, this is usually motivated by internal state of the animal. Where to move? Again, navigation capacity, then how to move, and all of these questions, these capacities are then linked by various movement processes. And once we get past this creates a movement path which tells you how or where the animal actually was. And all of this is influenced by external factors, and all of this in turn can influence the external factors back. So everything in this is connected. So this was on the animal side. Then on the human side, what we found was there was lots of different paradigms. So many papers describing paradigm for this, paradigm for that, framework for this, framework for that. One characteristics of this is that they are mostly much more specific than this one. So this one can be applied to any kind of animal movement study. This one here, these ones here are just very specific type of data, specific circumstances, specific methods. So there's much more fragmentation on the human mobility side in terms of theory. So we weren't really sure how would be able to connect this, but then what we found was this 4-step model, and this was actually a suggestion by a reviewer. So if this reviewer is by any chance listening, I would like to thank him or her, because this was a very, very good suggestion. So we found this 4-step model, which is a Eulerian analysis framework. And it's actually quite old. It's back from 1970s. I wasn't actually able to find the exact date when it was created. It just seemed to be used from 1970s on very widely. And what this one does is that it builds a transportation demand model based on flows, so on origin destination flows, Eulerian data. And what it does is it takes the set of traffic activity zones, so aerial units, or if you want locations in an area, and it takes the road network, and then it uses 4 steps to build this transportation demand model. And these 4 steps actually correspond to 4 questions that are very similar to the ones that we found in movement ecology. So in first step, the trips are generated, so the flows are generated between each pair of the units here. And this answers the question, why move? In the second one, sorry, actually, I made a mistake. This should be where to move, and this should be why move. So this is because it's 8 p.m. and I messed up the slides, sorry. Anyway, so first we say where do we move, right? So we define where do we start, where do we go. Then we run the spatial interaction model, which basically tells us why do we move, why is one location good and another one not so good to move to. Then we choose how do we go there. So this is travel choice, travel mode choice. So do we take a car, do we walk? And then finally, what route do we take? What route, how do we get from A to B on this road network? So this was pretty similar to what the animal framework was showing. And what we decided to do then is to put the two together, but also make it this more space aware, right? Because we are geographic information scientists, so geography has to play some kind of role. And in neither of the two paradigms, there was any role for the geography. So we came up with this framework here, which puts together the animal movement framework and the 4-step model. And it's the advantage over both of them or all the other smaller paradigms is that it's suitable for either animal or human movement analysis and either Lagrangian or Eulerian analysis. And so what we have here is that we extended that model of the individual moving into the question of who is moving, so we can have individuals, groups, or populations. Then we have the questions that were, questions 2 and 4 are the same questions as we find either in the 4-step model or in the animal movement model, with one exception that what route to take is not exactly the one, is not in the animal model, but comes from the transportation. But again, it is similar and it is relevant, so we added that there. And then what this does is that it creates a realized movement pattern, which is either a trajectory or flow or presence data, whatever kind of movement data. So this is all similar as it was in the animal movement model, and we also have the external factors in the same way. So the environment influences movement, but movement also influences the environment. But then we also added this geography here that we didn't, that other two models don't have it, which is what space am I moving in? So this then conceptualizes what kind of data you're using and what kind of phenomenon am I looking at. So do you have a 2D data, you have 3D data, 2D space, 3D space, continuous space, discrete space. Is it constrained, for example, if you're on a road network? And also all of these spaces and all of this analysis have inherent spatial and temporal scales. So for example, in animal movement, you can analyze movement at the step length or trajectory length or perhaps lifetime path. And on the human side, you can have like raw GPS trajectory, and then you can segment it into trips, and then or you can look then just at specific stop points and trips and so on. So all of that kind of thing. So what is the actual relation of your analysis to the space, and what kind of space are you using? What kind of scales are you using then comes in this bit. So that is the addition from the geographic information science into this mashed up ecology plus transportation model. And the advantage of this is that basically any movement study you have now, you can classify it based on this. So we have this as an example in the paper. We took 4 of our papers and basically just looked at how they answer all of these questions. And in this way, you have a framework where basically any movement study, regardless of the topic, can be compared to any other movement study. So that's my general paradigm, or our general paradigm. And now I will ask Jed to continue from here.
Thanks, Urshka. So I'm going to talk a little bit more about the similarities and differences in the different types of analysis. And if you've been to some of the workshops or meetings where like the cost action and some of the ones that were organized by Harvey Miller and Jennifer Miller in the United States, there was always lots of discussion about this in those kinds of meetings. And so that's one of the things we wanted to do in this paper, was to look more deeply in the literature to give those concrete examples of the exact similarities and differences that exist. So I'm going to not talk about the details so much here. You can read the paper and the supplementary material, but I'm going to highlight and flag some of the key things that I think are interesting here. So can you go to the next slide, Urshka? So I'm going to try and cover 4 main points here: the diversity of research objectives perspectives and methods that exist within movement analysis, some of the fundamental concepts and ideas. So the idea that there are some really core things that everybody is trying to do to answer certain types of research questions. And then I'll maybe highlight some, sometimes there are unique things that maybe don't, one group does that another group doesn't, and that's okay. And I think that's really interesting. So what are some of those unique situations that sometimes we encounter, and what makes them unique? And then lastly, of course, opportunities for innovation. So what are things that seem to be promising in terms of new ideas that may span across our disciplines that are interested in movement? Okay, next slide. Okay, so diversity of research. I think this was one of the main highlight points from the Miller et al. Paper that introduced this idea of the integrated science of movement in 2019. And Urshka's already talked about the diversity of frameworks that exist for trying to capture movement across the disciplines. And a lot of these papers are widely cited. So there's a lot of interest in this idea that, there is a diverse suite of, research going on using movement data, and there are lots of people that are interested in this from a variety of angles. And I think one thing maybe we don't do well enough is we don't celebrate the diversity of interests that exists within the field of movement science. And I think there's so many cool things. And this is a question that I continue to think about, is like, what's the application of movement data that I think is the most interesting, or maybe the most out there, to try and think about wow, that's a really neat idea. I never thought about how we could use movement data for that before, or that's just a really cool application. And it's really easy for me to come up with these. So I just scanned, some recent years of IJGIS, and I came up with all sorts of cool examples that are using movement data or movement kind of applications to study all sorts of different problems. So here's one that looked at basketball defense, so studying how good basketball players are at defending using trajectory data. Here's one looking at the spread of dengue fever using flows and using sort of movement along networks simulated in real data to identify optimal meeting locations. So if you have a group of people, where's the best place to meet up? And it factors in all sorts of contextual information and things like that. So all of these kinds of neat different application areas are using movement data. And I think that's something we need to continue to, not worry about, but actually celebrate. Okay, next slide, please. And through our work, we really did, and this was a long time coming. There really are some fundamental concepts and ideas that are being used in movement analysis. And so we tried to organize these into tasks and equivalencies. And I think Table 2 and Table 3 in the paper, and then the associated text in depth in the supplementary material, really gives you lots of ideas and specific examples of really, really strong equivalencies that exist along some of the core lines of questions across the human and wildlife movement analysis phase. So we talk about the idea of space use, or quantifying the spatial distribution of movement. Another really, really important one is the idea of segmentation or behavior analysis. So extracting behaviors or chunks of similar behavior from trajectories or other kinds of movement data. These are things where both or all sorts of applications of movement analysis, human and wildlife, are using. One of the ones I've been more interested in over time has been the study of interactions between moving objects, or group behavior would be another application that's similar. And I have an example from one of my papers from a long time ago, where I looked at a male and a female grizzly bear during mating season, quantified their interaction, and in the same paper also looked at an offensive and defensive player playing ultimate frisbee, again trying to quantify that idea of interaction to study those two things. A fourth one is understanding the context or environment and how those things influence movement patterns or relate to movement patterns. Again, this is being done in a variety of ways. And of course, I think as everyone knows, visualizing movement data, as you can see from these maps that are on the screen right now, visualizing movement data is not easy. And everyone in all disciplines that studies movement has struggled with the most effective way to do this. And so these are all areas that there are really fundamental lines of research that span across disciplines. Next slide, please. But at the same time, there's always going to be uniqueness. So not everything needs to sit in some of those tasks that we talked about. There are things that are outside of there, and there are also specific, species or applications or specializations where you're going to do something a little different. And as we continue to come up with new data and methods for analyzing movement data, I think there's going to be more examples that are maybe outside of our framework in terms of like they're just doing something very different. And sometimes it's not even necessarily the actual movement data analysis that is different, but maybe how you then link it back to context, or how you study the problem or answer the research question that you're interested in. So here's a recent example from my own research. So we actually use big mobility data with no individual information to study movement patterns during COVID. But because we have no individual information, we can't really make good sort of relationships about things like socioeconomic circumstances. So we aggregated the mobility data to aerial units in terms of our final analysis. So while all the mobility analysis that we did sort of pertains to all these sort of core ideas from movement data science, when you actually look at the paper, it uses spatial statistical methods that are really appropriate for aerial level data, which would be a little bit foreign or maybe unfamiliar to people who are more focused on movement analysis alone. So again, that sort of demonstrates that things don't always fit into these nice compartments when you look at an analysis or a research question in its whole. And so again, this relates to the previous question. I think there's like opportunities to use movement data in new ways to address questions that are different and unique. So what are some things that we're not using movement data for yet that we could be? Next slide, please, Urshka. And so this leads us to like opportunities for innovation. And this is where I don't think we have all the answers, and nor should we. So the idea that computational movement analysis is relatively new. But to quote Patrick Laube and some of the stuff he's talked about before, the low-hanging fruit is gone. So all of the like simple things that we can do with movement data, we've kind of done them all. So the opportunities for innovation, I think, are in coming up with new emerging problems where we can use movement data, are in thinking about new data and methods and how that can allow us to understand different types of patterns in space and time with movement data. All those kinds of things, I think there are still lots of opportunity for innovation. Okay, next slide, please, Urshka. So if the low-hanging fruit is gone, where do we go for next? And so this is what she was going to talk about, is the emerging research ideas and areas for new and innovative movement analysis. And so what are some of the fundamentally new questions we can tackle in movement analysis or in movement research using big data, using things like data fusion, looking at different spatial temporal scales? And so the one example I'd like to highlight that I'm sort of tangentially involved in is methods for starting to understand how human mobility or human activity are influencing wildlife activity. And there's a range of things that are going on in this sort of realm, from sort of small targeted studies at specific study sites to global types of analysis as demonstrated in some of these papers. So I think there's lots of opportunities there to use more and more types of movement data to study interesting problems at the intersection of human and wildlife movement analysis. So I think that's it for me, Urshka, and I'm going to pass it on to Shiwa now.
Yeah, thank you, Jay. Thank you, Urshka. So in this last part, I would like to talk about those things that Jed already mentioned a little bit. So this emerging technological trends that we can see in recent papers, but also problems and challenges that we are facing within this sort of integrated science of movement. Next slide, please, Urszka. So as both sort of Jed and Urszka already said, movement data is everywhere, and there are more sources of this sort of unusually big and complex data sets. They are just available for research everywhere. But what we have to remember is that movement data isn't really new, but just recently we've gained access to this massive amounts of data, and not only movement data, but also contextual data that goes with movement on really sort of high spatial and temporal resolution. Some of you may have heard of a sort of system called IJGIS, which is this international cooperation for animal research using space. It is a program that was initiated by Martin Wikelski and their sort of team in Max Planck's Institute, that seeks to attach really tiny transmitters that are less than even 5 grams, that they weigh less than 5 grams on millions of animals. And it has recently become operational. And what it allows us to do, it allows us studying animal movement, migrations, but also looking into this sort of great real-time biodiversity monitoring at a global scale, which is something that we weren't able to do before. What is also cool about this system and the tags is that they not only collect movement data, but also a series of information like temperature, pressure, humidity, but also other data from like magnetometers, accelerometers, and so on. And what is the way how this sort of system works, it resembles the idea of Internet of Things, where all the sort of animals and all their sort of sensor data is linked together, creating this amazing Internet of animals. And as we sort of have seen, especially sort of now during the ongoing pandemic, there have been sort of more and more movement or like human mobility data available. So we have Google and Apple releasing their aggregated sort of mobility reports. We have more and more mobile phone sort of companies selling aggregated to track or sort of various administrative units, either daily or hourly movement data they are just made available for research now, well, and businesses as well. And some of these data sets are actually shared as a special sort of on a spatial aggregate level, so as Jed shown, but some are rather raw and sort of just sort of slightly jittered, as you can see in this sort of image here with the trajectory from one mobile phone user in Auckland. So apart from this sort of amazing avalanche of mobility data that we are getting, there is quite a lot of contextual information that is available now. So we can build our own sort of homemade sensor-based devices to measure context, to measure high resolution, air quality. And we can either do it in our home, so like in the image here, taken by a colleague from UBDC in Scotland. And so we can build this fancy sort of boxes, and this actually box uses just a box from COVID tests, which is sort of nicely you're using, something that could be just rubbish otherwise. And we can have all these sensors there, and then we can attach this sensor to, e-scooters, bikes, and so on. And then we can get real-time information about the air quality while we are moving. So we are getting all this sort of detailed information about everything that moves and the places things move to. And because of the sort of amount of data we are getting, we have to remember there is plenty of noise in the data as well. So what comes to our mind, and the question we were sort of thinking about it, is to what extent and how detailed the movement data should be, so it doesn't have sort of too much noise in it. And do we always need data in this sort of very high and very high spatial and temporal granularity? Okay, next slide, Urszka. Please, thank you. So with this sort of abundance of sensors, multi-sensor platforms, massive amounts of data, and the developments and advancements in technologies like the Internet of Things as well. So this sort of increases, well, we can sort of see the increasing problem of fusing or merging all these data streams together in a reliable and meaningful manner. There is a need for new data fusion techniques that will allow us combining all the movement data with the contextual information that we are gathering. And here it's not only static information, but also this dynamic context that we are getting. And this could be the environmental data, it could be biological data, could be various information about activities that both either humans or animals are doing. And in case of humans, it could be also information about, social media posts or their sort of social media reality. So movement data as itself, it comes, as Urszka said, in two forms. So it could be either in Eulerian or Lagrangian representation. And there is still a massive scope for improvements in the way how we try to fuse different contextual data to different representations of movement. The other thing I wanted to sort of briefly mention is this real-time movement analytics. And it has been sort of emerging in certain sort of research disciplines, especially sort of in transportation, traffic management, with the advancements, especially now with the autonomous vehicle technologies, we can see that it's getting very sort of popular. It's less sort of popular and known and used for animals, but we can of course observe, where animals are in real time, but we don't do much sort of analytics, real-time analytics with them as yet. But what the main problem here is that we've been sort of mastering this linking historical data, movement data, historical sort of contextual information, but there is still really long way to actually long way to go to actually create proper context-aware models and predictions that can help us develop understanding and predict behaviors in real time. And the question here for us all is to think whether we need this context-aware real-time movement analytics and models to predict better things in real time. Next slide, please, Urszka. There is probably little doubt that machine learning has sort of become this sort of the big thing of the last couple of decades. And there are very simple, complex, and super difficult models that can be used to, in both animals and in both sort of animal movement research and human movement research for segmenting movement, classifying movement into different sort of travel modes for people, or whether the animal is sort of gazing, running, sleeping for animals, as well as predicting sort of what is the next place the human or animal will go and what routes they will choose. But with the growing sort of amounts of data and the amounts of this measurable context that we are trying to add to these models are becoming more and more complex, and they're often very sort of confusing. They are not transparent. So there's a huge potential of using machine learning and AI algorithms, but we have to do it in a clever way by trying to avoid sort of all the biases, incorporating expert knowledge. So not that you just apply random machine learning model on any of the movement data and sort of see some random results. We need to start collaborating more in between disciplines and listen to the discipline experts. And what's the question here is like, can we make these models actually sort of useful and understandable? And what are the questions, or what are the case studies or case uses of machine learning that we can still use in movement analysis? So sort of where we can go next with it. Next slide, please. So this is one of the sort of maybe not biggest, but one of the coolest sort of trends in research generally. So reproducible research is necessary to ensure that our sort of scientific work and work that we do can be trusted. And most sort of publishers nowadays are requiring already that the publications include underlying data, so the data that we use for research and code. And the reason for it is just to make it verifiable, and that we can, build upon what we have done already in the future. It's sometimes harder actually to do than it sounds, but this is the way we should be all going. In terms of data about animals are often sort of deposited and made available via repositories like MoveBank. And the human movement data are available as well to some extent via portals like Crowded, or you can buy them from companies like SafeGov, Uber Media, Near, and so on. The access, though, to individual human movement data is much more restricted because it triggers, a lot of privacy concerns. When we are sort of storing the data or working with the data or publishing the data, we have to remember that we should be doing it according to the FAIR sort of guidelines, so that the data is findable, accessible, interoperable, and reusable. And it's not only that we as people can reuse and do the data, but it's without any sort of, with minimum human intervention, you can download the process and access the data. It is also common practice these days that we share the code, and it's like however you like to do it. So whether it's a package or a piece of code, it's important to share it. And there have been quite a few, a couple at least, really good initiatives that help you guide through how to do reproducible science. And these sort of guidelines cover information about how to do data management, how to do the software development side of the things, and also how to sort of integrate different techniques within it. And the cool two examples are the one from the Agile sort of conference and how to publish in a reproducible way, and there is also a cool sort of guidelines on sort of scientific data, on reproducible scientific data science by the Turing Institute, and it's called Turing Way. It's really good, and I would recommend people looking at it. Next slide, please, Urszka. Thank you. So this is, whether it is actually a trend or it is a problem, it's something that we should probably be discussing. But geoprivacy is predominantly related to human mobility data. But of course, there exists obvious risk of releasing animal data and some animal data about endangered species, so poachers can track the animals and harm them, or we can the data will be released for some businesses on ecotourism, and then sort of the peace and quiet of animals would be disturbed by plenty of tourists trying to look at them. So there are some risk of it, but most of the research within the sort of geoprivacy has been done on the human side of movement. And integrated science of movement has this huge potential to help society to find solutions for sort of to the most sort of pressing problems that we are encountering in our lives. So it could be, for example, the human contract tracing measures. That this is something that we can think of, but this cannot be done without access to data. And so wide access to movement data is becoming increasingly sort of necessary and crucial. However, it's tricky to publish movement data without anonymizing the data first. Unfortunately, at present sort of state, there is no unique methods or technology or qualitative or quantitative metrics that could actually protect all anonymized data properly. And if there is always this issue of, if we anonymize data too much, the data it doesn't leave much utility for the data. So it's just too general to do anything with it. So these two figures on the slide show sort of sample data from Auckland, one mobile phone user, one showing raw data, just a little bit jittered, as you can see sort of nicely, the real trajectories of individuals, and the other image shows just the aggregate data to the spatial units, in this case administrative units of Auckland, showing the change of distance traveled within different levels of lockdown. So what we have to think of here is this sort of, where is the sweet spot between data privacy and the data utility? So for what sort of analysis, what data we need, and whether there is some sort of nice sweet spot that we can find. Okay, Urszka, last quick slide for me, please, now. So the science of movement is the study of both places, places where sort of people and animal visit, but also routes that we choose to take between these places. And these sort of simple concepts, they underlie most of the existing models or movement models that we use to separate movement from to separate movement into a set of sort of stops and moves. And in current research, we probably still know more about the movement part of the research, where still there is a huge potential in development on understanding what is happening in the locations that people or animals are staying. And there's recently been a trend in looking at it from the more sort of placial, personal way of looking at things, and it opens sort of opportunities to look into more sort of quantitative aspects of the place that people are spending time in, or animals, as well as this qualitative information that makes location more personal. And we have to remember that a movement is, both spatial and temporal process, and it should be studied as such. So time should never be forgotten or neglected. And we as sort of GI scientists have this advantage of sort of being able to develop different sort of robust and spatial temporal models that are actually contributing to, that could be applied to both human and animal research. Movement comes at different scales. So all of us talked about different types of data, and they come in different forms, shapes, different spatial and temporal scales. And what we have to remember that depending on the scale, we will have a different, we can get different patterns and different sort of results based on the scale. So there's something that we shouldn't be forgetting. And you can see on the sort of images at the bottom with sort of two different trajectories that the different sort of spatial and temporal scale of movement is visible in there. And the last thing that I want to talk about very quickly is that movement data is very useful. It is super sensitive, and it's very, very precious. And precious because it's sensitive and because it's expensive. And it is a golden egg of current research. The only problem with it is that it leads to disadvantages, because some people have the data and have access to it, some don't, which means that we quite often are actually unable to reproduce the fancy method that have been done in the past, and we not always are able to compare these things. So there is a huge need to generate synthetic mobility data sets. So something that represents sort of or creates the same sort of set of statistics to describe the collective or individual population without actually releasing the real information about people. And synthetic data sets, they can provide, and they already have started providing, this sort of common ground against which we can test different computational methods where we can get them tested, validated, and they can just nicely reflect the characteristics of real data sets. Gosh, I almost did it in 13 minutes rather than 11. Sorry, Urszka, for that. But that's it. That's me.
Yeah, so thank you, Shiva. So that brings us to the end of our part, and now this leads to your part. So throughout this presentation, we posed these questions. They are also copied in the chat. So what we would like to do now is to hear from you. So if you have something to add to this, something of interest, if you can answer any of these questions, if you can give us examples of how you dealt with any of these cases, so we would like to hear from you. And I think May is usually
no, let's look at very.
So I will pass over to May.
Thank you. It really should be a very flexible and open space for discussion. So anybody have idea would like to share or question would like to ask, please feel free to open your mic and videos, and so that we can start the conversation. And usually people starting shy, and then in the end we run out of time. Yes, Song, please go ahead.
Hello. Yeah, thank you. Thank you for the speaker. Yeah, very insightful, exciting presentation today. I read this article before, but yeah, definitely today's presentation helped me better understand the topic. So my question is, because as a GI scientist, In addition to the proposal of the new theory methods, such as the integrated movement framework, I also wonder how the proposed integrated framework can support the development some of those analysis tools, or also response to the reproducible research question. Because, for example, I remember I think 1 year, 2 years ago, there was an article about the detection of the home range, also with some code or package available. I wonder how the new framework can also support the development of the integrated analysis for both human and animal movement. Yeah, thank you.
So who wants to take this? Shall I?
Well,
Before the response, I really want to support Gao's proposal to have maybe a community-driven platform to develop a movement package to allow tools and method development for the integrated movement science. I think in computer science, they have a common community effort to building tools or platforms or libraries, and this could be a good opportunity for GI science community to work together on this. So sorry, Jed, go ahead.
Yeah, so thanks, Song. I think some of the first thought that came to my mind was, I think one of the things when we think about developing new tools for movement data analysis is, before we do that, we need to think about what question are we trying to answer with those tools. So tool development for the sake of tool development doesn't really get us anywhere necessarily. So maybe with this framework, we can start to categorize and, zero in on, how tools can be related to specific types of research questions. And then once we know what that is, we can start to say, okay, what types of questions could it be used similarly across the disciplines? So that might be the first thing I say. The more pragmatic question is, I think you're right. I think we're seeing in Python that people are starting to build sort of from the ground up, from fundamental objects that can be used to analyze movement data. And then once we have those, we can start to build on top of those packages that do specific tasks. And I don't know, in R there has been some work on that, but it has been more fragmented, as R typically is quite a fragmented computing environment. And I can't speak about anything other than R and Python, but I think those are things that I think we need to think about as a community, is maybe we don't start just at the methods, but we start at fundamental data objects and packages that we can then build on top of with our more advanced methods and tools. But I think maybe the best answer to your question is that methods for the sake of methods doesn't really get us anywhere. I think we do need to be framing it in terms of questions, and I hope our framework can help people do that a little bit better.
Yeah, I thought that the framework already provides the 7 basic questions for movement analysis. And so that with that 7 questions, what are the objects or representations required? And then what are the methods to can use to analyze or compute those objects? And then I actually have another thought along this, is that I'm sorry, probably related to one of the questions about method and data as well, is that the examples you provided are animals and human, but there are other things can move, are not animals or humans, right? So for example, storms, wildfires, or heat wave. And I think the difference is that the animals and humans that we consider as a point, so we don't need to worry about dimensionality or shapes. But when we're looking at wildfires or heat waves or storms or hurricanes, they have variations of shape and sizes along with the movement. And I think, is that something part of the conceptual framework you propose, or it should be additional to the conceptual framework you propose?
Well, that's an interesting question. I don't think we've considered that in this case, because as you say, it was more like for point objects which are moving, and then we look at the characteristics of that. But I think that's a very, very interesting question. I would say, however, that I have seen analysis of hurricanes, possibly because they are also there's a set of trajectories that's very easy to obtain, and anybody can basically just download it from the internet, and then you can run all sorts of Lagrangian analysis of that, because they're basically trajectories. And I have seen a lot of this kind of analysis where basically they just consider the hurricane as a point rather than as an object with space and shape and extent and density and everything. So I think it boils down to how you represent whatever that is moving. And I don't, in this framework, we were not really looking at, like you say, wildfire. That's like a changing area that not just moves, but extends and shrinks and starts and dies and so on. So we were not looking at movement like that.
I think also if I can add.
Yeah, I apologize that Harvey have his hands on for a while, so I really like to have his input. Sorry. Hi,
thank you. Oh, no worries. Hi, thank you. Can you hear me?
Yes.
Favorite Zoom or Teams question these days. Great presentation. Thank you. Every time I read this paper or see it presented, I like it even more. So nice job, folks. May actually asked a question I was going to ask. What are the boundaries around this integrated science of movement? Would it include like things without intention and preferences and behaviors such as storms and wildfires? I'll move on to, so that's a very good question. Another one I want to ask, or I want maybe just kind of explore a bit, is I think one of the great unsolved problems that we see in something like time geography, of course, my favorite topic besides bicycles, is emergence. Is how do we, from individual to collective, emergent patterns, and that's still part of that agenda that has not really been addressed adequately. Like, how do all these individual space-time movements coalesce and turn into a ballet, as Hagerstrand termed it, into emergent properties? And how do we connect those two levels? And I really haven't seen in all these years much progress on that part of an analytical framework for movement science. So I'd like to hear your reactions to that, please.
I think that's a very, very interesting topic. I have actually seen quite a lot on collective motion done in physics and ecology lately. So I think there is potential for connecting things. So for example, here in St. Andrews last year, we had a seminar by Orit Pelek, who is a physicist, and she is modeling collective motion and collective behavior of fireflies. And I know that in Max Planck Institute for Animal Behavior, there is the group that is looking at collective motion of all sorts of animals. So a recent application I saw was using machine learning to identify individuals in a herd of African animals in the savannah, and then predict how these trajectories are going to move in this, like a herd-like motion. And there are physics groups in Rome, I think, that are looking at collective motion of starlings. So I think on animal side, there is actually quite a lot done in this kind of research, where you have a lot of individuals moving and being affected by what is the nearest individuals, and then building something that otherwise would not emerge, like, I don't know, murmuration of starlings or whatever. But I don't actually know much about this on the human side, and if there is a potential of linking of animal to human, or is there a potential just, within various animal collective motion topics. I don't know.
I want to say I'm thinking beyond just the mesoscale, like schooling and flocking behavior, but how do larger, like, societal and economic dynamics emerge from individual movements? And that's what Hagerstrand was talking about. He actually talked about, space-time dynamics from the individual to the project to the meso to the macro level. How do we connect it all the way up? Whether that outcomes are economic behavior or maybe like a landscape change in the case of animal movement. That's something I've been thinking about for decades. I haven't made any progress.
Yeah, I don't have any answers for you, Harvey, that's for sure. But I think one thing I don't think we do well enough in the movement analysis field, or whatever you want to call it, is in other sort of types of studies, they look at thresholds and tipping points a little more effectively, and maybe there's some things that relate to spatial scale or temporal scale that are like key tipping points that sort of, thinking about, how long a day is and things like that, and how far we can move in a day or a month or a week or whatever, and how that relates to those macro scale patterns that arise from individual patterns that we collect data on. So maybe there's something in that arena that we could start to explore, but I've never done it, so I can't say I have any insight.
Yeah, same for me. Probably not too many insight, but I was thinking about it for a while as well, and like whether there is a way of nesting different temporal and spatial scales to this sort of bigger horizons, or looking from the smaller scale and trying to answer the sort of smaller questions, and then like how we can fuse it and fuse the nested both temporal and spatial scales together. So just like whether there is a way for it, but haven't figured it out.
Well, thank you. Really, really good work. Congratulations. Really enjoying the thoughts that you guys are stimulating through this. So thanks.
Well, actually, thank you for your paper, because that was the sort of trigger that we came up with this one.
I'm triggering. Yeah, I know. Thanks.
Yeah, well, thank you, Harvey, for the excellent question. I look forward to your next paper to talk about from individuals to collective and then to system level dynamics. So that will be your test. We look forward to your manuscript. We have Federico's hand. Federico, I apologize if I pronounced your first name incorrectly.
Don't worry. And thank you very much. It was extremely interesting to listen to this. I'm a movement ecologist, so I'm a bit outside maybe of in the group of people. I have a couple of comments. The first one is about what you were discussing before on forms of disturbance like wildfires, hurricanes, and so forth, and how to integrate these in the analysis. I mean, I haven't a direct experience on that, but if I think about this as a movement ecologist, probably I would say it depends from the scale at which you want to go to get the response from the animal. I mean, if we think about wildfires, which is something on which I'm probably going to work in a while. If you're interested in something like a sort of longer-term recolonization pattern by animals of burned areas, probably this can be treated as something like a fixed polygon. While probably the things change when we want to analyze something like an immediate response of the animal to the disturbance itself. So I don't think there is a unique response in this sense. It's probably always a matter of scale, as you have highlighted for several other case studies throughout the presentation. I don't know if you have any further thoughts on that. And then I close a completely different point. I was thinking about the discussion and about I was particularly impressed by the question about the artificial intelligence, which is something that indeed we are going to use, and we are going to use more and more for a specific tool that as movement ecologists to be used, that is camera trapping. So one question is, how do you foresee the future of camera traps data within the unifying paradigm that you have presented? Sorry, this was long.
Yeah, can I go on camera traps? Is that, yeah. So we mentioned camera traps there, but they're sort of a bit on the side of this Lagrangian Eulerian data types, because in general, I mean, they can create trajectories between camera traps if you can identify the individual. So if you know that the same animal is on this camera trap and on that camera trap, and that can also give you flows, because you know how many animals actually went from one camera trap to another camera trap, but you have to be able to know that this is the same animal. So it may work for animals that have unique patterns, like zebras. I think you can identify from photos that is the same individual. Or it would work if the animal had a GPS on them, so that, you know, again, it's the same individual between them. But if you have animals that you cannot tell, this is the animals, this animal was here, this animal was there, then you cannot actually create movement data that would be representable for either this kind of analysis, for any of this kind of analysis that we are discussing in the paper. So I think camera traps are sort of a different problem. That said, I think machine learning or artificial intelligence is an extremely good approach to analyze these data sets, because these data sets are typically really big, because you can get hundreds of thousands of photos. You can have like an array. Actually, we had me and Jed were supervising a PhD student who was doing camera trapping in the Scottish Highlands. And Jed, how many camera traps did she have? Like 15 or something? And she ended up with 15. And she ended up with 800,000 photos that she had to analyze by hand, right? There's like no, and you know, and this was from like one summer. And so this is just no way that this can be done by people if you want to scale this up to any kind of analysis. And so you have a lot of data. And on the other hand, machine learning and artificial intelligence or neural networks are really good at identifying objects from images. So this is one of the applications that has actually been studied a lot, and a lot of methods have been developed to this. So I think Shiva was looking for good case use studies for machine learning and artificial intelligence. I think this is one of them. And there are actually some algorithms that already exist for this, and some tools that already exist for this, but I think we're just at the beginning. And an additional complication is if you don't just have photos, but if you have videos. So if your camera trap doesn't just take a photo, but whenever it gets triggered, you know, it takes a 10-second video. So again, no way that this can be done manually if it's being scaled up the way it's being scaled up. So, and again, a really good case study or use case for artificial intelligence.
Yeah, and I would build on that and say, actually, I think there's lots of good evidence that AI or machine learning type methods are going to be really helpful in generating movement data from video type data sources. So, for example, from aerial imagery or drone-based imagery of urban settings, or in the African savanna, or on a penguin colony, or of a soccer game. Like, we're already collecting video with drones on those types of applications. We're going to be continuing to do that more and more. And I think these types of methods will help us convert video or picture type data into trajectories that we can maybe then go back to our other types of methods.
Yeah, thank you very much.
Well, thank you. Last call for questions or comments. Okay, and I will.
Wait, can I make one more first, May?
Oh yes, please.
Speaking of AI and machine learning in this context, there's a lot of talk right now about things like physics constrained AI in earth science, like constraining when we try to search use artificial intelligence, machine learning to look through massive Earth systems data, to constrain the search based upon what we know is realistic and what isn't. And I think there could be a role for mobility researchers to contribute to this in AI and machine learning and looking at movement data. There are things we know are possible and not possible, and I think that's something that we can really add to this. Because you're right, if we just leave it unconstrained, we can get nonsensical answers and even trivial answers. So that's just one comment. It seems to be something that's really big in the geophysics field right now, is because they're exploring machine learning and AI like everyone else is. That's just a comment I wanted to make.
Yeah, so we have sort of raised it as well, that it's cool and it's nice and you know, getting this sort of complex models running and going, but just incorporating this expert knowledge in them from the start. It's the way sort of forward. And like you said, constraining it to the limitation, not limitations, but just to the limits of what it actually is feasible or not from the start.
Thanks again.
All right. Well, thank you all, and I will save the recording and post that in the YouTube channel. And so for people who could not join us today, and they were still available for them at the YouTube. And I hope that we will continue the discussions on the YouTube channel. And I trust that the author will welcome your correspondence, email them or ask them questions through our meetings or either virtual meetings or in-person meeting in the coming future. Well, thank you all. I hope to see you next time in our IJGIS webinar in November. Thank you. Bye-bye.
Thank you for having us. Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye.
Do we wait or no? We just go. Okay.